who goes where. That's why, do you know where this guy went in this? No idea, it doesn't really matter. It's just, these are obstacles, push people away. To get, so in my example, I'll keep pushing guys away to get the girls into the right place. I don't really care what I did to the guys, which guys I'm pushing. As long as the girls are in the right place, I have solved my problem. Okay? Right? So, this is a new kind of a puzzle problem. This is an abstraction of the original puzzle problem that you probably didn't think about. The kind of abstractions you thought about were act as if tiles can just jump to the right position, in which case that would lead to missing number of misplaced tiles thing. Or act as if tiles can jump, but they actually have to, they can get to the right position through the other guys, but they have to move legally. In which case you get the Manhattan distance heuristic. But this one is also an abstraction. This is a very different kind of an abstraction. This is what I'm saying that abstracting a problem can be an art form in itself. Computing this distance, that is, if I have these guys like this and I need to get them here, you do know you can solve it, right? If I give you this puzzle, and if you have a bunch of time, you can keep moving around the white guys, until the red guys get to the right place. And you count the number of moves you make. And what I'm asking is, what's the minimum number of moves you have to make to get this configuration to this configuration? And if you count that, that would be guaranteed to be a lower bound on the true distance. Very impressive. What's more interesting is that if you actually compute this for this, you will get that you need 31 moves to go from this configuration to this configuration in this particular problem. 31 moves. That's a much bigger number. Remember, the bigger the better, as long as you are reducible. You see what I'm saying? So you can imagine that people who use pattern database heuristics will do much less search, because they're still admissible, but they have bigger numbers for the heuristic pattern. Now, the interesting question is, how would I compute these numbers? For any, so assuming this is my pattern, I will need, for any arbitrary configuration of these red tiles, because the pattern making tiles, I need to know what is the minimum number of moves to get here. Right? This isn't like just counting the number of tiles, or counting the number of places each tile has to go, which is what you're doing which is what the misplaced tile and Manhattan distance heuristic. This actually is a search problem by itself. So here is a cute idea. What exactly would be the best way to compute this heuristic? One thing you realize is heuristics have to be computed for every node. It's an upfront work for every node. Whether it actually occurs during the search or not, you basically assume that anything can happen during the search. So for every possible crazy configuration of these red tiles, I need to know how long do I need to get here. Okay? This stuff is, by the way, what I'm about to talk about is a second order complexity, because this is telling you how to compute this heuristic. Okay? I'll tell you a simple idea, which is concept done by you. Because the first idea will always be done by you, unless you're answer. The first idea is, for this, I can actually set up, a search for this. Start from here and write this as the goal node. I mean, goal node only checks if the right guys are in the right places, and then just basically do some sort of a search problem. Now, here is a crazy thing. That search, you can do misplaced tiles heuristic to do that search. So you're doing original search. It required a heuristic. To compute that heuristic, you're doing another search, which uses another heuristic. That can happen. And in fact, using misplaced tiles heuristic is actually better here than in the original problem. Right? You see what I'm saying? So this is a reasonable idea. You could start for every, basically your search algorithms right now are asking, get me the H value of the current configuration. And you have a little piece of code that is just computing it quickly at that time. Just counting the number of misplaced tiles or counting the number of moves you will make. Right now, this little piece of code will be a much bigger piece of code that actually has to do search. And it will take a couple of minutes or maybe more, depending on the efficiency of your computation, and it will give you a number. And then a little later, another configuration will come where let's say maybe 12 is here, and then this is right now, and then I need to again figure out how to go from there to the correct configuration. And I keep doing this every time. The computer scientists among you must be realizing that if I'm doing so many times for every strange configuration of this, how to get here, this is sort of like all sources, single destination, shortest path problem. All sources, single destination, shortest path problem. In those cases, it typically makes sense to not go this way, go the other way. Do you see what I'm saying? Because the work that you did, for example, in going from here to here, much of that search may well be repeated when you have a slightly different thing where 12 is here and the blank is here. That's so closely connected to the previous search, but you would act as if it's a completely new search and redo the whole work again. This is where computer science part of your background should come. You don't want to redo work. How do you want to avoid redoing work? You start from here. You start this as the root node. And do horrors of horrors, breadth first. Okay? What you do is you start from here, you do breadth first search. So you start moving blanks around, right? And every time you move blank around, then essentially if you get, let's say by the 7th level, the first time is when, let's say the 7th level is the first time when you see a particular pattern, then the cost of going from that pattern, that configuration to this is 7. Because if it was fast, it could have done lower than 7 moves, it could have come before the 7th level. This is the breadth first idea. You basically pushed the breadth first under the bus long back because you made fun of it, saying it's the stupidest thing anybody can do. It's not the stupidest thing if you have to find the value for every possible configuration of these red lights. Because then what you're trying to optimize is not a single search, but a whole collection of searches. And it's much simpler to start from here, do a breadth first search, keep generating new patterns as you go from here, you will keep getting, as you start doing breadth first search, eventually this pattern gets displaced. Whenever it doesn't get displaced, you get a new configuration where the red lines are. And you say, whenever you see the configuration for the first time, you have a database. This is the word pattern database comes from. In a database, you will put for this configuration, this is the number. That's it. So you might spend a whole bunch of time computing the pattern database mistake. And then the original search will just zip it. And in fact, for puzzles like 36 puzzle and so on, you can't even solve them without using pattern database tools. Because it turns out the minimum essentially involves doing this more interesting things. Yes?
When we are doing this backward breadth first search, when is that going to stop? This is the like the start node, and what is the goal?
You can that's a very good point. So basically, you would stop when you have found the values for every possible configuration, and you can using elementary combinatorics, you know how many configurations are there. So you know the database is saying here are all the configurations. Put numbers for them. Okay, and whenever you see one of those configurations in the breadth first search for the first time, you go put it in the database. Look how far we have come from yelling at the breadth first search and acting as if heuristics are just extremely easy to compute simplistic functions. to some things where the heuristic itself is a very hard search problem, which may itself actually can use heuristics. Although in this particular case, I decided not to use heuristic. Instead, I just actually use breadth first search because I'm computing all sources, single destination, shortest path. That is much easier to do with all destination, single source, shortest path. Okay? This is how we are connecting your 3-term life. If you had a 3-term life, this is data structures, and yeah. Okay? You can't forget the cardinal sin of computer science, which is to repeat work. There better be a very good reason to repeat work. Okay? Any other questions on that stuff? Okay. So the last thing I want to say about A-star search is this ID A-star search thingy. I'm hoping, how many of you have actually saw the ID A-star in one of the videos? I forget. Raise your hands with confidence. The rest of you probably just saw before, I don't know. So all ID A-star search is supposedly doing is to do A-star search without exponential memory. Exponential time cannot be avoided unless you have perfect heuristic. Exponential memory is something that you can avoid because if you do depth first search, you can avoid, you can get by with linear space. So ID A-star does basically do A-star what IDDFS does to breadth first, essentially. Okay, so what you wind up doing is you have a tree like this. IDDFS did like this, right? It would basically put like a depth limited contour, and you get a little tree. And that you do what search? DFS, right? So, and then if you find the solution, you stop. Otherwise, then you extend it by another depth, one more depth, okay, one more level of depth, and you get a new tree. You do again DFS. Did we or did we not violate the cardinal sin of computer science that I just talked about 3 seconds back?
Yes.
The smartness of computer science people is they're willing to violate their cardinal rules for good reason. Okay, in this particular case, IDDFS actually does re-expand some nodes more than once, but there is a bound. It only re-expands a node at most d times, where d is the total depth of the tree. And we are doing it with our eyes fully open, not because we are drunk, but we have our eyes fully open and we are still doing it because there is a greater good. What is the greater good?
Memory.
I'm reducing the space. You see what I'm saying? So there may be sometimes when you do repeated computation, because of the interesting trade-off, in this particular case, the space can be reduced. Right? Okay, that's IDDFS. Fine? The question then is, how does it become IDA star search? IDA star search. It too should have some sort of a lines that needs to be some sort of a contour. Who would be the contour depth for the IDA star? What is the equivalent to the depth in A star search? What is the equivalent to the depth in A star search? What? The F value. So, you do IDA star search by essentially increasing the F contour limit. So first you start with F contour limit to be F0, and every search node which has an F value less than or equal to F0 is part of the current tree. Then you increase it to F0 to F1. Okay, and F1 is the next F value. Okay? And so when you do this, the contours, suppose this is up to DFS, so the contours for IDS, the IDA star look sort of like that. The red ones are the F values, and they don't have any connection to depth, because the depth of the node and its F value are not proportional to each other. Because what matters is the F value, and F value depends on the H and G is the edge cost, and H is the heuristic estimate of the distance to go. So for example, I can have situations like this where essentially irregular shaped contours. And this contour, this is f of 0, this is f of 1, f2, f3, etc. Now for under each contour, now I will have to search. So for example, when I have at one point of time, at the third iteration, I will have this tree, right, under this contour. I have to search that tree. So I would use A star search with a good heuristic, right? If IDA star doesn't use A star, what's the point of the word? Hit yourself hard on the back of your head and forget that. IDA star should never use A star search in individual iterations. In fact, the only search strategy that gives you linear memory is depth first search. So the greatest gotcha question about IDA star, and I'm giving it away, is IDA star does depth first search, A star search in each iteration. Looks like a pretty reasonable thing. I mean, why would anybody have named an algorithm IDA star if it isn't doing A star somewhere? If it does A star, you will get all the problems in A star, which is that A star doesn't have linear memory. It makes no sense to use A star in each iteration. You have to use depth first search. One of the things I'm a big believer of doing the stupid thing and telling your brain not to do it. Okay, because if you just get it right the first time around, you probably don't realize how lucky you are. And so you're more likely to make the stupid mistake later. So it's very important for you to say, I almost fell for, individual iterations of IDA star being A star search. Better not do it ever again. Because after all, it makes no sense. A star search it's not guaranteed to take linear memory. So it does that first. IDA star does in each iteration depth first search. Suddenly it's as if it's like the revenge of the empire, right? The old empire. Previous iteration I said depth first is used to compute the pattern database heuristics. Now I'm saying even after A star, depth first is being used as part of IDA star. They never go away. They have good properties. Okay? So in fact, depth first search is what is used in each of the iterations. What else do I need to tell you to do IDA star? So start with F0, which will be the F value of the, presumably the root node. The question is, what is F1? In the case of IDDFS, D0 is 0, that's the 0 depth. D1 is 1, D2 is 2, D3 is 3. What is F0? F value of the root node. What is F1? If you don't know that, you can't write the algorithm.
The next largest F value.
What you need to do is you keep track of, so basically the way you are deciding so you put a bound, F bound, and for each search node that basically you say, oh, sorry, you are above the F value bound right now. Next time, right now I'm not going to deal with you. And you throw them out, right? That's what you do. But before throwing them out, you remember their F value. And you want to remember the guy with the minimum F value who still couldn't make it in the current iteration. That's the guy who was like so close to the gate. And you didn't let him in because, sorry, you're more than F, my current F value. So when I increase the F value, I need to get that to be my new F value. This should both give you a sigh of relief that I have figured out a way of getting F0 to F1 to F2, and a huge sigh of disappointment. Because it looks as if the way I am saying, I'll be expanding the F value to get the next guy who just got thrown out in the last time around. What if that's the only guy who comes into the tree now in the next iteration? Then the number of iterations would be equal to how much? For IDDFS, how many were the number of iterations? D, right? The total depth of the tree. So there were D number of iterations for IDDFS. But here, if every time the closest guy who could get in winds up having an F value that nobody else has, then that's the only guy who gets into the tree. So the tree now has increased by one node. One more by one more node, one more node, one more node. So how many iterations will there be? B power d iterations, which is actually n is the number of nodes, but it's equal to b power d because d is the depth and b is the branching size. This would kill you, like completely kill you. I understand repeated work can be, kind of justified sometimes, but not the repeated work that exponentially many times repeatedly expands the same node. So what's your hope? Your hope is that when you let that closest guy who couldn't make it in the last iteration in, he or she comes along with a whole bunch of their friends, all of who have the same exact F value. Otherwise, you would not get them in. Do you see what I'm saying? Which means the worst case scenario is for every node to have a unique F value. If every node has a unique F value, IDA star is the dumbest idea on the planet. It will take very little memory, but on the other hand, you will never get that. Okay? This is something that you need to understand. Normally, IDA star works because, the F and H values tend to be, for many, for example, for the 8 puzzle problem, they're integers. So there are fewer buckets. And more things just have to fall into the same bucket by the pigeonhole arguments. But if I basically wind up having a real value F value, which is, two real numbers are never almost never equal. Two real numbers, right? They're almost never equal. Then you're screwed. Because every time one extra node will come in and you will do b power d iterations, and that's just no fun at all. Okay? That's IDA star search. Two important things to remember. IDA star doesn't do A star. It only is inspired by A star. It just uses the F value. Very confusing, but just like uniform cast search doesn't actually deal with trees with only uniform edge casts. Uniform cast search is the name for any tree with non-uniform edge casts. And IDA star doesn't do A star. And for a good reason, because it does A star, it doesn't get linear. Okay? And that it can do too many iterations, and that could be very bad. And a third, more interesting problem with IDA star that actually has solutions is that if we are way beyond the time when Bill Gates said nobody needs a computer that has more than 640K bytes of memory. Bill Gates actually said this. And then he went on to make the Windows that just keeps bloating, right? Bazillion gigabytes. So we are past that. We actually have pretty huge amounts of memory on our machines. The memory is a funny thing. If you needed one extra byte more than what you have, you die an ignoble death. Just die. Right? Segfar die. If you don't use all the memory, you don't get any batches. Who cares? It's like, basically I have friends who actually clean up their Gmail box, for example, so that there is less clutter in it and more space is free, as if those free bytes are having a great time in Mill or something. You don't get a batch. If you try to go over the Gmail limit, you are dead. If on the other hand, you only keep one mail, just you're worried that maybe I'll never, like somehow I'll get a batch, I have the least amount of memory. So remove every mail other than the last one. That way you'll have very less amount of space used in Gmail, but that's not actually a particularly smart thing to do. Linear space is too little space. Everybody has way more than linear space on their computer. What you really would like to do is what I do with my Gmail. Actually, what I do with my Gmail is slightly different. When I run out of space, I pay and get more space. You can do that too. Okay, you can do that too in this day and age. But the other possibility is, basically, if you have like one of these, klutzy Macs with 128 gigabytes, you keep filling it up, and then when it says you're dangerously low on memory, you stop doing what you're doing, try to remove a whole bunch of things. And there is extra 3 bytes, so you continue working for 3 more minutes, and then you say dangerously low on memory, and you do this again. Okay, that will be too much of a thrashing. Or when it says you're dangerously low on memory, I spend some time and remove 20 gigabytes of stuff. Typically mostly class-related emails. And then for about 5 days, I won't again do disturbed. Why not do that for A-star search? Which is, keep letting I'll give you a limit on the open list size, 10 gigabytes. Okay? So you keep filling the open list until 10 gigabytes. When it reaches, 10 gigabytes minus 1 search node size, then you panic and you try to remove some of the guys from the open list. Just like I removed some others. And sometimes when you remove files, you have to recreate them. Sometimes when you remove nodes, you may have to reevaluate them later on. But this turns out to be a much better idea than being extremely conservative and having only 1 or 2 names in your Gmail account or 1 or 2 files with the rest of the hard disk extremely nice and shiny with empty bytes. You see what I'm saying? That idea is actually described in the textbook, and it's called SMA star. And you can see that there would be some interesting issues there in doing it. In particular, you need to kind of decide which nodes will have to can be removed. Like for example, when the machine says you are about to run out of memory, to me, I don't just remove the file I'm currently working on just to make space. That's like extremely stupid. I know that anything I remove I may have to recreate, but this one I have to recreate like right there. What would you do, for example, least recently used files? The ones that I haven't used, 2006 class emails. Yeah, what the heck, hopefully they're never going to come and ask me again about this emails. Remove them. Right? Least recently used. What else, by the way, does this remind you of, assuming that you're all computer science students?
Hash.
What? Paging strategies in OS. Least recently used. Paging strategy, for example. And in fact, you can also talk about nodes that are likely not to ever be expanded because they're so far down the open list because their F values are so bad. Those are the ones to get rid of first. So you can write the algorithm yourself. In fact, you can read the textbook. It's like multiple pages, explains some interesting, bookkeeping you have to do to decide what you can do. Okay? Okay. So what I am going to do in the next minutes is I will just show you one example of min-max search and we'll continue with this. Okay. So in game trees, typically we'll talk about it a little more. Actually, by next class we will watch the rest of you also watch the video I asked you why. In game trees search, there is 2 agents, not single agent, 2 agents. So the max basically makes a move, and then basically min gets to make a move. So you call these agents A or B, you call it max or min. Okay, max is our guy typically, and we want our guy to be. Okay, so max makes a move, then min gets to make a move, then max gets to make a move, then min gets to make a move, and there are certain game configurations that are known to be a win for max, that are known to be a loss for max, and there are also goal configurations which are known to be loss for max. That means you can't go any farther there. And that is where the example that I'll show you here. One of the greatest games, of course, is the tic-tac-toe, right? And so it's a 2-player game. And so basically, so this is Max, our guy, and Max basically gets to put R cross in any of these places. And then at that point, min gets 2. So again, the way the game works is that max puts their crust, then min puts their dot, then max puts their crust, and min puts their dot. And then there's this very complex set of rules about how tic-tac-toe works that I hope you have figured out in grade school. If you're not from US, then look up Wikipedia. Okay. Essentially, you want anybody who controls an entire row, column, or diagonal bits. Right? That's the basic idea. Okay, so in terms of search, so the way to play, tic-tac-toe, of course, is that you can just put your class, when you were in grade school and somebody told you this, unless you are like, Gauss or Einstein, you probably say, let me start playing, let me put my class right away. And then they'll put their dot, and then you put your class, and then you put your dot, and after a while, one of you lose, and then you start all over again, but you're not particularly learning that much, you're not all that right. Okay, but eventually you figure out that there are some heuristics. And in fact, the heuristics comes from the fact that you realize that this is a game, and it's not just you playing, the other person also gets to play. Games are unfortunately bad just because of the opponent. You can win chess without an opponent extremely well, if you can play both sides. Okay? So it's the opponent that makes the game hard, right? And so what you do in search, in trying to figure out your move, you start from here, you consider all your moves in your head. You consider for each of the moves the opponent's response for each of those moves, possible responses. For each of those, your possible responses. For each of those, your opponent's possible responses. The deeper you get to see the game tree, the more information you have about the game, because some particular move might look nice and shiny at the top level, but as you go down, you will find that if you make that move, you basically lose. Every possible way of playing the game after the move, you lose to a loss. And you figure that out, in essence, by going to in the most simple min-max search, you expand the tree until the leaf level, where every node is either a known loss, known win, or known cloud. So for those of you who understand tic-tac-toe, this is a loss because dot guy already got this column. And cross guy is our guy. And this is a win because essentially, this is a draw because nobody controls anything. This is a win for you because you control this diagonal. So based on what is happening at this bottom level, you need to decide what move you should do. Unlike a search strategy where you get the entire path and start doing the moves one after the other, here you make your first move and wait for the opponent to actually decide what they're going to do. Okay, so what I'm going to do is show you this, and then you go off, and next class we'll come back and talk more about this. So imagine a crazy tree like this. So this is the max, this is the min board position, this is the max position and min positions. At the bottom I gave some numbers. Those numbers, I'll say this is the game, these are all terminal positions. And